Today's lesson needs to be titled Definite Integrals and Riemann Sums. Definite Integrals and Riemann Sums. It's a much longer title, but I'm not going to write anything more than that. Definite Integrals and Riemann Sums. Okay, a couple weeks ago we learned what a Riemann sum was. Who in here can tell me what a Riemann sum is used for? Why did we need to learn about them? What did they help us do? They helped us find area under a curve. It was an estimate, right? And what shapes did we use? Two different kinds of shapes. Trapezoids and rectangles. Rectangles and trapezoids. When right and midpoint sums were rectangles. And then we learned the trapezoidal rule, okay? Now, those were only estimates, right? They weren't exact. They were close, but they weren't exact. Then we learned about this thing called a definite integral. And then we learned that if it was a geometric shape, yeah, we could find the exact area. And then then we learned how to use the first fundamental theorem of calculus to find the area as well. But now I want to talk about how to find exact area with Riemann sums. Okay? So, I want you to picture in your mind some random graph in the first quadrant, some random graph. Just picture one in your mind. If you went from 0 and you broke it into 10 rectangles, you could probably get a pretty good estimate of the area. Do you agree? If you broke it into 50 rectangles, it would be better. 100 rectangles would be even better. 1,000 rectangles would be even better. What would be the best number of rectangles to do? An infinite number of rectangles, right? So basically what you're picturing is a rectangle where the width is basically as small as your pencil tip. So if you took an area and you drew with your pencil vertical lines all the way down, you would get an exact area under that curve pretty much, wouldn't you? Okay, that's what we're talking about today. We're going to have an infinite number of rectangles under a curve represented by a Riemann sum that is actually a definite integral. So we're looking at how to write a Riemann sum that represents a true definite integral. We're going to go back and forth between the two. On the board it says we're going to convert a definite integral to a limit of a Riemann sum and vice versa. And we're going to go back and forth, okay? Now, we're going to write down a lot of stuff, mostly because I'm going to explain it today and it's going to make sense, but 2 months down the road you're going to go, wait a minute, how did you get that? Bear with me as we write some verbiage on this paper. But first of all, I want you to remember a few things to make these formulas make more sense. Remember a few things. Okay, the first thing we're going to remember is from the Riemann sums page. How do we calculate delta x? This was on the second video of Riemann sums that you watched. Do you happen to remember what the formula was? It has a's and b's in it. Do you remember? It is b minus a over n, exactly. And please put in parentheses if the intervals are equally spaced. It's something we talked about when you did the Riemann sums worksheet, but it's something good to remember now. The intervals have to be equally spaced, otherwise that delta x doesn't work. Today's they will be. So we're going to be using delta x quite a bit. Okay. The second thing I need you to remember is something you learned in pre-cal, and we've alluded to it a little bit when we did the Riemann sum notes, and that is this. What is that called? That's called a sigma. I want you to write at the bottom k equals 1 and put an n on top. Now n could be 3, 4, 5, 6, 7, doesn't matter. And then out to the side I want you to write k squared. Now, what does that mean? What is this k equals 1 for? That's where you start plugging in numbers, right? Okay. Let's pretend for a minute that n was 5. Would I plug in 1 and then 5? That's it? 1 through 5. So this is kind of like an A and a B. It's starting and stopping. That's what it's for. And that's how the sigma turned into the integral. So this means plug in 1, then 2, then 3, plus dot, dot, dot. And you add them all up. What is the one before the last one going to be called if the last one is n? N minus 1. So n minus 1 squared plus n squared, and then you stop. Okay? So you need to be familiar with that, because if we're going to be adding up a bunch of rectangles, especially an infinite number of rectangles, we don't want to write an infinite number of terms down. We want to write it in as short a method as we can, and we're going to use this. Okay? So please write the following. A definite integral is the, quote, perfect Riemann sum. It is the perfect Riemann sum. In other words, it is a Riemann sum that perfectly fills the integral up. There are an infinite number of rectangles with a very tiny width under the curve. A definite integral is a perfect Riemann sum. There are an infinite number of rectangles with a very tiny width under the curve. Now we're going to draw this out in just a minute, and we're going to construct the Riemann sum formula from our drawing. Okay, it's going to look a little complicated. Just try to stay with me as much as you can so that you can understand where this formula that's just extremely ugly actually comes from. So first thing I want you to do is draw a first quadrant over here, kind of a long x-axis. I want you to mark off two kind of far apart marks. The first one has to be off the y-axis. So this is 1, this is 2. And we're going to draw some random curve over the top. Doesn't have to be the same as mine. It could be close. We're going to call this curve f of x. And I want to, using these infinite Riemann sums, I want to find the area under that curve from 1 to 2. So I'm going to draw a line at 1, draw a line at 2, talking the area of that thing. Can you write for me what the definite integral would look like for that problem? It would be an integral from where to where? 1 to 2. What goes here? F of x, because I don't know the equation. And then, is that it? No, I've got to have a dx. Now, what is that dx for? This right here is the height of each rectangle, because it's the y value, and the dx is the base. Because dx, remember, is the same thing as delta x. And delta x is the width of each subinterval. So this is basically the same notation as this sigma up here, just written in a different way. Okay? So it's base times height, which is area. So the next thing I want to write down is this, and this is kind of important, so I'm going to put a star by it. To create an infinite number of rectangles, comma, we need a limit as n approaches infinity of the sum of the rectangles. Since we can't plug in infinity, the only way we can do it is to do a limit as n approaches infinity. So our answer is going to look like, it's going to have a limit notation and then a sigma right after it, because it's saying I'm going to get infinite rectangles that are all added up. So every answer is going to have a limit and then a sum right after it. Okay? So we're going to kind of draw this on here. First thing I need to figure out is what is delta x in this case. For this specific problem, we wrote at the top of the page that delta x is b minus a over n. So in this case, what is b minus a? What number? it's 1. So it's 2 minus 1 over n. We're leaving that as n because it's going to be infinity later. So this is 1 over n. Now, that represents the width of each rectangle. This is the width of each rectangle. So, I would love to just draw in line width rectangles right here all the way across the page, but you wouldn't be able to see what I'm doing. So what I'm going to do is quote unquote zoom in, and I'm going to put spaced apart marks, even though we're picturing, it's like we zoomed in on that thing and it's much wider than it really is. Now, this right here, the distance between the marks is 1 over n. So each one is 1 over n wide. Okay? So now I need to figure out what the x values would be at each mark across the page. X values will be what? Now this is where the thinking is going to need to take place. I need you to think about this. If this is 1 and the width of this is 1 over n, what is the name of that point right there? 1 plus 1 over n. Does that make sense to everybody? So 1 plus 1 over n, comma. What would the second mark's name be? 1 plus 1 over n plus another 1 over n, right? So it would be 1 plus 2 over n. Do you agree with me? Is everybody seeing how I'm getting this? What's the next one? 1 plus what? 3 over n. Now I don't want to list them all. Tell me what the last one would be. 1 plus what over n? N over n. Now think about it. What is n over n? 1. What's 1 plus 1? 2. Isn't that the last number on the interval? Yeah. See how that works? Okay. So there are my x values. And why do I need those? Because I can't find y values unless I know where the x values are. And the y values are going to give me my height. So the y values will be, okay, my function in this case is just called f of x. So if x is this, y would be f of this. Do you all agree with that? So f of 1 plus 1 over n, f of 1 plus 2 over n. I'm going to skip the 3 over n because I need the space. And then f of 1 plus n over n is the last one. Okay? These are my heights of the rectangle. That's the height of the rectangle. Whoops, I'm off the page. Sorry about that. Okay. Now, in a minute, I'm going to have to write it as a summation. So I need to pull this down for a minute, take a look at that summation. Now notice that this thing has a k in it. So k happens to represent 1 for the first term, 2 for the second term, 3 for the third, and so on. Does that is for each term? Yeah, the numerator is. It's 1 and then 2, and the next one would be 3 and then 4 and so on. So that numerator is going to turn into k. It's going to become the k. So I need to rewrite this a little bit differently. So just bear with me. I'm going to basically factor the numerator off and write it like this. F of 1 plus 1. Now that seems a little bit redundant, I know. But that I'm doing this for a reason, comma. Thank you. F of 1 plus 2 times 1 over n, comma. If I was to write down the exact next one, it would be f of 1 plus 3 times 1 over n. But I'm going to skip over to the last one, f of 1 plus n times 1 over n. Okay. Now the 1, the 2, the 3, up to n, those are my k values like I said. So now I can actually put this in a minute into the summation, but I've got to talk about what the area is going to be. So the area of the rectangle is going to be what? Okay, these are the heights. Here is the width, or the base. What's the formula for the area of a rectangle? Just base times height. So let's pretend for a minute that this right here is my first rectangle blown up really wide. Okay? The base is 1 over n. The height is the y value right there. Do you agree with me? The next one. The base is still 1 over n. The height is the second y value. So what we're going to do is we're going to write it this way. It's going to be the base, which is 1 over n times f of 1 plus 1 times 1 over n, comma. What am I doing? I'm just taking this answer here, putting a 1 over n in front of it, because that's the base times the height. Do it again. 1 over n times f of 1 plus 2 times 1 over n, dot, dot, dot. I'm going to squeeze the last one in. 1 over n f of 1 plus n times 1 over n. Ugh. This is college math. And professors will just write the stuff on the board and go, yeah, you get it, don't you? You're looking at it going, no, I don't really get it. But now I want you to stop for a minute. Do you get where this is coming from? This is the base. That's the height of the first rectangle. Base, second rectangle. Base, last rectangle. And all the ones in between. Okay. Now, I don't want to write all that out. That's too much writing. So let's write it as a sum. So the sum will be, let's do it this way. It always goes k equals 1 to n. Now remember, the number in front of this parentheses right here is k. Before I write it down, the 1 over n is going last. Just bear with me, I'll show you why in a minute. So we're going to write f of 1 plus k times 1 over n. Isn't that true? Every time I change, the only thing that's changing is k. Right? K is first 1, then it's 2, then it's 3, then it's all the way up to n. And then I've got times 1 over n on the end. Now, that's a big jump. I want you to stop and look at it. Just really look at it. This is the way you got to do college math. Sometimes you just sit there and stare at it for a while. I was doing this last night with grad school. I had to finish a program on a computer to make it work. And on the way home, I figured out my problem. I figured it out. But just look at it. Do you see how I got from this line to this line? If you talk to your table, does everybody understand? Y'all get it? Look at each other. Yes, no, maybe so. If one of you gets it and the other one doesn't, help them understand where everything comes. This is your height. This is your base. This is add them all up. That's what it is. Okay. We're going to write it another way. Let's come back together, please. What does 1 over n equal? What did we write from here on the screen? What do you see that 1 over n is another way to write it as? Delta x. So I'm going to change the way it does it in the formula. K equals 1 to n, f of 1 plus k delta x times delta x. That actually looks a little not so scary. Okay, but one thing I got to talk about right here. Where did that 1 come from? Go back and look at the picture. Where did the 1 come from? It's the starting point of my rectangles, right? So, please make yourself a note. This is not always going to be a 1. This is what A is. That's going to be A. Okay? So now we have built the formula for Riemann sums. If you don't completely understand what I've done right here, you can still do the homework, I promise. But what we're going to do now is we're going to write this down as the formula, the official formula that's on the worksheet. Okay, is everybody done writing this down? Because I got to go to a new sheet of paper. Okay, the official formula. Is as follows. Big star. Big star. So this is easy. The integral from a to b of f of x dx is equal to, okay, because I said we're going to have an infinite number of rectangles, our answer must start with a limit. Limit as n approaches infinity, then the summation. K equals 1 to n. And then what comes after it is what we wrote right here. F parentheses a plus k delta x times delta x. Okay. If you don't completely understand how that came to be, that's all right. You can still do the math. It's just like yesterday. If you didn't completely understand how the second fundamental theorem works, you could still do the math. Okay. Now, the first kind of problem we're going to do is take a definite integral and turn it into this. And I'll walk you step by step through it. Here we go. Example. We're going to take the integral from 0 to 3 of x squared minus 1 dx, and we're going to turn it into a limit. Limit as n approaches infinity. Summation k equals 1 to n of what? Okay. Every single limit problem starts like that. Has the limit and has the sum. You just have to figure out what comes after it. Okay? Let me show you how to do it. All the pieces are hidden in that integral. Okay. Step 1. First, find delta x. Okay. What's the formula for delta x again? Look at the beginning of your notes if you don't remember. You need to know this, guys. B minus A over N. Do you know what A and B are? They're right there staring you in the face. So 3 minus 0 over N. N is going to be infinity eventually. So this is 3 over N. There's delta X. So when you go to write this side, you're going to put 3 over N where both those delta X's are. Okay? K is going to stay K. Now we got to figure out the rest of this stuff. Step 2. Then I've got to figure out what A plus K delta X is, because that is what's getting plugged into the function. What is A? What is A? Look right here, guys. What is A? A is 0. Remember, A is the bottom limit of the integral. 0 plus K times, I just figured out delta X is 3 over N. Does everybody see where I got all this? Clean it up. So K times 3 over N is 3K over N. This, put an arrow, this is plugged into F as X. That is what is going to go into the function as X. So the right side of this sum is going to be something that looks like this, but X is not going to be X, it's going to be this fraction right here. So we're ready to write our answer down. Our answer for this integral is the limit as n approaches infinity, summation k. Now, look at the function in here. Draw your parentheses. I don't use x, I use 3k over n. So I'm going to write 3k over n in place of x. Then it says squared. Then it says minus 1. I'm going to close my parentheses. And remember that dx is the same thing as delta x. What's delta x? 3 over n. That goes right there. You're done. Questions? Okay, right now I want you to pull out your worksheet. Pull out your worksheet. I want you with your table to do number 1 at least. I'd like you to do the first 2. Follow these steps. See if you can find delta x, then write what a plus k delta x is, and then write the equation. All right. Let's talk about how to go the other way. So, on your notes, draw a line. Now, this next example, it is critical that you copy it exactly the way I write it, because one drop of parentheses could throw off the whole answer. So, we're going to go from limit form back to integral form. So, k equals 1 to n. I have the limit as n approaches infinity, k equals 1 to n. That's one of the ugliest summations I've ever done. Bracket, parentheses. 2, another parentheses. K over n, the quantity squared, plus k over n, close the parentheses, and then open another one times 1 over n, close the bracket. I'll give you just a second to write that down. I don't want to read it again. You just need to look at where you are and make sure you copy it exactly as I have it. What does this equal? Now, I think about half of you in here, if I left you alone with it for about 5 minutes, you could probably figure it out on your own. But I'm going to go ahead and explain it to everybody so that you get it. Some of you might be able to get part of it. Like, oh, I kind of see something. Okay, looking at that problem, what do you see? What do you know? Do you know what delta x is?
Yes.
Yes. Where is delta? What is delta x?
1 over n.
1 over n, because it is at the end of the problem. So the first thing you do is write down what delta x is. It is 1 over n. Okay? Very helpful. I need that. And it's almost the same steps as before. Okay? Now, in order to do this problem, I need to know what a and b are for my limits of integration. Do I know what a is? What is a? A is 0. A is 0. Do you know how I know a is 0? There is nothing in the parentheses with k over n. If a was anything else, it would be k over n plus 1, k over n minus 3. If a was anything other than 0. There's no number added to k over n in its parentheses, so a is 0. Okay? So a is 0. And knowing that, I can actually find b. So the limits of integration are from 0 to what? 1. How do you know it's 1? Because this top thing is b minus a. So b minus a has to be 1. Isn't that how you found the top of delta x? You subtracted your limits of integration? Yes. So if you know the bottom one, you can figure out the top one. Okay. Now, I'm going to write myself a note here. This is b minus a up there. Oops, drew that the wrong way. And that helps me find this. Later on, you're going to go, wait a minute, how did I get that 1 again? Because the top is b minus a. Okay. Now, once, like we did on the other one, we got to write down what a plus k delta x is. Now, I know a is 0 plus k, and I know delta x is 1 over n. So this is k over n. Y'all agree with me? This changes to x in the integral. Now, when we went the other way, we took all the x's and changed them into k over n. Now we're going backwards. All the k over n's are going to turn into x's. So we're ready to go. So let's integral. What are my limits of integration again? 0 to 1. So now what we do is we come back up here to this long summation, and we're going to start copying it down. You don't need the brackets. You just need the parentheses. Everywhere you see a k over n turns into an x. So it's going to say 2x squared plus what? X. Close your parentheses. Now, 1 over n, is delta x, and delta x turns into dx, and we're done.